Download this code from codegive.com, link in the description below. Arena allocation and function coloring, preventing unnecessary colorization. Function coloring, also known as function specialization, is a compiler optimization technique where the compiler generates multiple versions of a function based on different usage contexts. One common cause of function coloring is the type and lifetime of data passed to the function. Arena allocation, when used correctly, can often prevent unnecessary function coloring by creating a uniform memory management strategy, particularly when dealing with dynamic allocations inside frequently called functions. This tutorial explores how and why. Understanding function coloring. Imagine a function process_data that can receive data allocated on the stack or on the heap. If the compiler can see that in some call sites it always receives stack allocated data, and in others it always receives heap allocated data, it might generate two versions of process_data, one optimized for stack data, potentially faster access, no need to check for null pointers if guaranteed stack, and one optimized for heap data. This is function coloring. While potentially improving performance in specific cases, excessive function coloring can lead to code bloat, larger executable size, increased compilation time, and even cache misses if the duplicated functions are frequently switching in execution. How arena allocation helps. Arena allocation helps mitigate function coloring primarily by 1. Uniform memory management * instead of mixing stack allocation, malloc, new, and custom allocation schemes, arena allocation provides a consistent way to allocate memory. This uniformity can prevent the compiler from differentiating between call sites based on the allocation method used for input data. 2. Lifetime management * arenas offer a predictable lifetime for allocated data. All memory allocated from an arena can be released at once when the arena is destroyed. This contrasts with individually managed allocations, example malloc/free or new/delete, where the compiler might need to track individual object lifetimes within the function, potentially leading to coloring based on how those lifetimes are managed. 3. Alignment and padding. Sometimes some arena allocators provide more predictable alignment and padding characteristics compared to other allocation methods. This can further reduce the potential for specialization based on memory layout. A practical example, C++. Let's consider a simplified scenario in C++ where we have a function that processes data. Explanation * data versus arena data * the data struct uses std string, which internally manages dynamic memory for the string data. This means that instances of data may have their string data allocated on the heap, even if the data object itself is on the stack. Arena data, on the other hand, avoids the std string and uses hr * that points to memory allocated within the arena. Arena allocator * is simple, and non-thread safe. Arena allocator is provided. It allocates a chunk of memory and then provides memory from that chunk on request. The reset method effectively deallocates all memory in the arena at once by resetting the current position. A more sophisticated allocator could manage multiple chunks and handle out-of-memory scenarios more gracefully. *create_data_ functions ***. These functions illustrate the different allocation methods. Create_data_on_stack creates a data object on the stack. Create_data_on_heap creates a data object on the heap. Create_data_in_arena creates an arena data object, and critically, allocates the string data within the arena. *process_data_naive versus process_data_arena*. These functions process the different data structures. Process_data_naive takes a data by const reference, and process underscore data underscore arena takes an arena data by const reference. Asterisk main function asterisk the main function demonstrates how the data structures are used. Notice how the calls to process underscore data underscore naive are with data allocated in different ways, whereas calls to process underscore data underscore arena are called with data only allocated from the arena. Why arena allocation reduces coloring asterisk. In the above example, without arena allocation, the compiler might see that process underscore data underscore naive is sometimes called with data objects where the string data is on the stack, because the data object itself is on the stack, and sometimes with data objects where the string data is on the heap. This difference could prompt the compiler to generate two versions of process underscore data underscore naive. With arena allocation, process underscore data underscore arena always receives an arena data where the name pointer points to memory allocated from the same arena. The allocation source is consistent across different calls. The compiler is less likely to specialize process underscore data underscore arena because it sees a uniform memory management strategy. The address passed in for name in arena data always comes from arena allocator. Key advantages of arena allocation for reducing coloring asterisk. Asterisk controlled allocation asterisk arenas ensure that all memory is allocated from a single source, making the allocation pattern predictable. Asterisk bulk deal location asterisk the entire arena can be released at once, simplifying memory management and reducing the need for fine-grained lifetime tracking by the compiler. Asterisk localized data asterisk objects allocated from the same arena tend to be close together in memory, which can improve cache locality and further reduce the need for specialization. Asterisk customization asterisk arena allocators can be tailored to specific application needs, such as alignment requirements or memory access patterns, optimizing memory performance and reducing specialization triggers. Considerations and trade-offs. Asterisk lifetime management asterisk the lifetime of data in an arena is tied to the lifetime of the arena. This means you need to carefully manage arena lifetimes to avoid dangling pointers or premature deal location. Arenas are best suited for scenarios where the data has a well-defined scope, example processing a request, rendering a frame. Asterisk thread safety asterisk simple arena allocators are typically not thread safe. If you need to use arenas in a multi-threaded environment, you'll need to implement appropriate synchronization mechanisms, example mutexes or atomic operations. Some pre-existing arena implementations already handle threading. Asterisk fragmentation asterisk arenas can be prone to fragmentation if objects of varying sizes are allocated and deallocated frequently. However, this is less of a concern if the arena is reset as a unit, or if the allocation patterns are relatively uniform. Asterisk error handling asterisk arena allocation needs to handle out-of-memory situations. The provided example uses a doubling strategy, but more sophisticated error handling may be required in production code. Asterisk code complexity asterisk implementing and managing arenas adds some complexity to your code. You need to weigh the benefits against the increased complexity. Beyond the simple example, choosing an arena allocator. The simple arena allocator in the example is for illustrative purposes only. For real-world projects, you should consider using a well-tested and optimized arena allocator library. Here are some popular options. Boost.pool Boost.pool provides a variety of memory management tools, including pool allocators that can be used as arenas. Boost is a mature and well-respected C++ library. EASTL, Electronic Arts Standard Template Library. EASTL includes an arena allocator designed for game development, focusing on performance and memory efficiency. Custom allocators. You can create your own custom arena allocators tailored to the specific needs of your application. This gives you the most control over memory management, but it also requires more effort and expertise. Look into STDPMR, polymorphic memory resources, in C++17 and later for a more generic way of working with custom allocators. This allows you to more easily swap out allocators without major code changes. How to verify the impact of arena allocation? The best way to confirm that arena allocation is preventing function coloring is to 1. Examine assembly code *. Use a disassembler or compiler explorer, like Compiler Explorer at godbolt.org, to inspect the generated assembly code for the function of interest. Look for multiple versions, specializations, of the function. If you see only one version, it suggests that function coloring is not occurring. 2. Use profilers *. Use performance profilers to measure the execution time of your code with and without arena allocation. A reduction in code size or a performance improvement can be an indicator that function coloring has been reduced. 3. Compiler flags *. Some compilers offer flags that control function specialization. Experiment with these flags to see how they affect the generated code and performance. For example, in GCC and Clang, you might use no inline functions called once to prevent inlining and specialization of functions that are only called once. Conclusion: arena allocation is a valuable technique for optimizing memory management and preventing unnecessary function coloring. By providing a uniform and predictable memory management strategy, arenas can help the compiler generate more efficient code and reduce code bloat. However, it's important to carefully consider the trade-offs and choose an arena allocator that is appropriate for your specific needs. Remember to verify the impact of arena allocation using assembly code analysis and performance profiling to ensure that it is achieving the desired results. Always consider thread safety if applicable to your use case.